Okay, class. This particular talk is over aspects of experimentation and data and numbers and basically the groundwork for doing inquiry. By inquiry, it's a fancy term for asking questions, investigating where you start in natural science. To be clear, I want to start talking about the role of some of these terms, what they do for us, with this subject of natural science. And I keep saying it that way because natural science, if you can go with me with this, is a type of philosophy, is a style of thinking, is a habit of questioning that has very particular rules to it. Things can be sciency or scientistic or something like that, but not actually doing science. Science, philosophically speaking, is inductive reasoning. Now, I don't know where y'all are at with logic and if you covered deductive versus inductive, but deductive is going from a large concept and applying it to individual cases. So I could say all teenagers are, and then fill in a blank, and then I would go down the list and say Connor is this, and Clay is this, and uh, Nadia is this. And so I could just start applying that general concept to all of you. That is, in a negative sense, one of the problems with stereotyping is that you take a large concept and apply it to individuals. Inductive reasoning is going in the opposite direction, where you take small little observations, one by one, and then maybe if you get enough of those, maybe you can make a general statement. That's really hard to do and it takes a long time. So it's going from small to big. So deductive reasoning is from big to small, big concepts applied to individual cases. Inductive reasoning is individual cases eventually arriving at a larger statement, which is hard, which takes a long time. Science is inductive, and so we want to talk about the role of this thing called an experiment. If you're savvy enough with logic or philosophy, in philosophy or logic, what is a syllogism, right? A statement or a claim of logic. Well, that's been abandoned in science in a way, and instead we have the experiment. Right, so that's what I want to talk about. This is a type of thinking, and it's very particular. Now, sometimes science very much works like this, and it looks kind of like a hot mess. It's all over the place. It is a kind of an ugly process. It's very intuitive, very human, and just goes round and round and round. Y'all are taught that science operates this way. The reality of how it feels is like this. And so, what do we do with the difference between this and this? The best way I could tell you is that this is the way science actually works. A scientist can have a love of, say, orca, and they just love killer whales. They could have been thinking about something before bed and had a really weird dream. They could have some sort of hunch or intuition, or they might just be really curious or interested in something. Typically, what they don't do is they say, you know what, in order to do science, I'm going to go out and observe something, and then I'm going to ask a question, and then I'll put forward a educated guess, which I can't stand that phrase, and on it goes. And then I'll design an experiment and buy my materials. And that's the way we're kind of taught that it's supposed to happen. But really, it's more like this. So the difference between these two is this is how science feels to an individual. So if you're going to do science fair this year in high school, if you're going to try and conduct a line of inquiry that's unique to you, that you want to do, this is the way it'll feel. And that's okay. Everybody's okay with this. And you're gonna ask questions, and I don't know what I'm doing, and feel like I'm all over the place, and generally it'll get better and better. But this is the way it feels. This is what we use, I would say, to communicate science. So when I'm not you, and when it comes time to understand how your brain worked, and you want to convey, like share with me, this is what I did, then you got to clean this mess up. You got to clean it up and give it to me this way so that I can try and understand it first, repeat it second. So that's the difference. These steps right here that you're taught nice and clean, this is for science communication, science sharing, and it's the cleaned up version of what you went through. So in your notes, let's make sure you have today's date, and we're talking about the role of experimentation and measurements in science. But in your notes, let's get some definition terms down. The first term that I want you to get is hypothesis. No longer do I ever want to hear in this class or anywhere that a hypothesis is an educated guess. It is not a guess. Scientists don't guess. Or they might guess, but you know what you call that? Guessing. That's really it. A hypothesis is a statement, a claim that can be tested. We have to be able to test it. It's an explanation for a formal question, right? That can be tested. We can determine whether or not that particular hypothesis is true or false. And hypothesis literally means underplacing. Can your statement, can your explanation hold up under the weight of the phenomena? And if it supports it, then it might be closer to being true, and we keep testing and testing and refining and refining. So that's what a hypothesis is. It is not an educated guess. Okay? So if I ever ask you a question in class like, why does this happen, or why are things like that, and I'm not being punchy, I'm just trying to give you an example, people could say, well, that's the way it is, or God did it. And neither of those statements, for example, are testable. You could say it's random, and that's fine, I guess, but we can't test randomness. We can't test the divine, and we can't test just it is what it is. That's not a statement. So we have to be able to do something with that statement beyond just listening to you say it. And the something that we do is called an experiment. An experiment is a procedure that puts pressure on, puts weight on, tests the hypothesis. We are trying to make it fail. We're trying to prove it wrong. We don't just want to confirm what we already think. We want to see if we're wrong. Is it okay to be wrong? Absolutely. As a matter of fact, professional scientists will tell you they are wrong, they fail 90% of the time. The sad thing is that in a science class in a school, we can't really allow that, even though that's the way the science actually works. So it's okay to be comfortable with that. That's the way science is. And so anyway, we're going to test out your hypothesis. And when it means under controlled conditions, it is very difficult to test the reality of natural phenomena, the causes of natural phenomena out there, quote unquote, in the world, because there are too many variables, too many things flying around. So we have to bring it into the lab, not to make it perfect or sterile or fake, but to try to reduce the number of variables, which I'll explain in a minute, reduce the number of things that might be affecting that natural phenomena. We're just trying to focus and make it simple. So when people sometimes criticize science and say, well, lab science isn't real, it's not that way in nature, the scientists already know that. They're trying to get it as simple as possible so that they can see what's happening and find a cause. They're not under any delusions that what they're doing is how it happens in the natural world. So understand that. It's under controlled conditions. So speaking of controls, make sure you're writing all these down. If you need to go back through the slides, you can. The control is different than controlling things. I know it's the same word, but a control is something that you're not doing anything special to. Now, you could put it in the fridge, put it in the sun, or keep it at 73 degrees, or whatever you want to do, but that's it. You just know um, what its conditions are, and you're not going to change those conditions. And the reason you're doing that is because you have another situation that you are going to change radically. You're going to boil this one, or put it in the dark, or hit it with strobe lights, or whatever it is that you're doing, and you're going to measure the crazy one against the control. Okay, the weird one that you're doing everything else to, you're going to measure it against the control, not against what happens in nature, but against your control. So inside of that, you have two different types of variables. You have independent and dependent. Independent variables are variables that you are in charge of. You can decide which way they go. Dependence, well, it depends on what happens. So to give you an example of this, let's pretend you're going to boil water. What are the variables that you are in charge of? What decisions are you making? The size of the pot? How much water to put in? You're not really in control of the time. If you want to see how long it takes to boil, are you in charge of the heat? Not really. You're in charge of the dial that turns the heat up. It's that specific. So you turn the dial to 5 or 10 or low or high. You are in charge of that dial. You're in charge of the size of the pot. You're in charge of how much water you put in. Maybe you can think of a couple others. The things you're not in charge of are the time it takes to boil. That's a dependent. We're waiting to see how long it takes to boil. The temperature of the water itself, you're not in charge of that either. So if you measure it every 5 minutes, then you take a temperature reading. Okay, so the things that you're in charge of, those are your independents. They're independent of anything else except you. And the dependent variables are the things that you're measuring. So what do you master and what do you measure? Those are your independents and dependents. The next definition that I want you to have is theory. When people say it's just a theory, they're misusing the term. To say that something is a theory means that it is an explanation supported by a large body of evidence obtained from many different investigations. So in other words, it's well supported and well established. So when we get to like evolution, you'll probably hear this the most. People will say, well, it's just a theory. Thank you, it is. And what I don't really hear from folks when we talk about cells is that they say, well, it's just a theory. It's just cell theory, if that helps you put it in perspective. A theory is something that's well attested over a long period of time by a lot of evidence. And so the reason that cells and evolution are called theories is because life is found on no other planet. If we should find life on another planet, and it is composed of basic units of life like cells, and it's undergoing a process of development over time, like what we describe in evolution, well, then those will go from theories to laws. But right now, we only have theories because Earth is the only place. We only have a dot. We need two dots to make a line. So I hope you understand that. That's how that works. And so, speaking of laws, laws are general descriptive statements about natural phenomena that should be applied everywhere, at least everywhere that we know in the universe. We've seen it beyond just Earth or beyond just this one scenario. There's very, very few laws, like law of gravity, right? And there's a law of thermodynamics. So these are general universal descriptions of how quote unquote natural phenomena work throughout the universe. So this is a graph from your book, And what we want to do is practice, and we'll talk about this. We'll talk about this in class. I want to have several slides of graphs and data that I want to go through with you, but this is one. And we want to learn not only to pick the right answer, but how would we describe what's happening in this experiment to these little paramecia, these little single cell creatures, as temperature goes up. So I think in your notes, what I'd like you to do is pick one, A, B, C, or D, right? But in class discussion, I want to talk about what happens when that blue line takes a nosedive at the very end. So have something ready for that. Another example of this could be how camouflage works. So these mice are the same species, found in two different places there in Florida, near Florida. One's on the light sandy beach, other one's on the dark grassy area. They're the same species. One mouse is pretty much white with a gray patch. The other mouse is brown but has a white patch on its belly, which means something. That brown mouse, for example, to get your brain going, is not camouflaged all over, only on the top, which means this has something to do with something above him that's trying to see him visually, not smell him, but see him from up above. And so this is going to have to do with predation and how camo actually works. So we'll talk about this in class, but I want you to go ahead and see it. Here's our basic control. We put a light mouse on light background and a dark mouse on dark background, and then we switch the two below. Those are our variable experimental groups. We want to see what happens, and no real surprise there what happens. You can see how the graphs are inverted, and then if you're a dark mouse on a light background or a light mouse on a dark background, you're going to get picked up more often by a predator. That's pretty easy to understand. But if we make it a little more complicated, right? Like if we put these two types of mice on two types of environments, but then we change the light levels. Like we go to nighttime, that's one change. And then we have a full moon versus no moon. This is what we'll talk about in class. This gets really confusing, and we have more questions that come out of this. But what we want to do is try to make a statement about how camouflage works. So I will bring this graph up in class, and we will talk about how camo works. We're going to come up with a statement. You are welcome to stare at this graph, hit pause later on, come back and play it and hit pause, and come up with a statement beforehand. But I will tolerate some minutes of silence on our shared discussion online to where I want you to try to come up with a graph, and I will call on you to share your statement with the class. So just get past that shyness stuff, and we want to see how these statements come out of our mouth, and we want to bounce them back and forth to each other because that's what scientists do, and we want to see what's a good way to talk about camo. Okay. So as we collect data, we want to start getting real savvy on describing the data and using basic units. This is not anything I'm going to go over at length in this class because you should have had this in middle school already. But your base units in here are meter, kilogram, second. We don't really use amps. We measure in Celsius, not Kelvin, and not Fahrenheit. I mean, we'll grab a Fahrenheit reading just for comparison, but we're going to try and stick to Celsius. We don't really worry about light intensity, and in candles, moles might be something we do if we do some chemistry. You should know your prefixes in the metric system and what they mean. As a matter of fact, you're going to watch a really weird 1970s creepy video on powers of 10 that's got wonderful music. Not really. But it'll be something that you'll get a kick out of. It's a little bit cheesy, certainly dated, but you'll have fun learning about the powers of 10 and how that matters in universal measurements. I think, what did y'all learn about this? Something about King Henry died of chocolate milk or something? I can't remember, but there you go. And then last, if you're algebra savvy, you need to learn how to convert from Fahrenheit to Celsius, because I think we're the only country, if one of the few, who still use Fahrenheit. So know how to convert between the two. If you memorize the formula for one, you automatically know the other. You just have to keep your order of steps uh, where they need to be in order to go through. So Celsius equals Fahrenheit minus 32 divided by 1.8. But to go the other way, Fahrenheit, basically you add 32, right? Um, and multiply by 1.8. So just know how to go back and forth between the two. That's it, folks. I want you to prepare for a discussion if I call on you of those graphs. You don't have to be right and you don't have to be perfect. We just want to use our minutes, have a good time chatting about how what camo does and how to interpret those little paramecia dying off at the end so that we can have a good discussion time.